A hardware and software integrated power optimization approach with power over simulation at SoC. That's right. Complexity of the system on chip is increasing exponentially with advancement and artificial intelligence, machine learning, and IoT technologies. Keeping up with the latest trend in ASIC domain, advanced low-power design is a major requirement in high-performance SoCs. The increase in power layers and power ports combined with the requirement for a faster power up and power down process has resulted in adoption of the increased hardware control compared to the software control. The increase in the hardware controls for the identification, verification, and analysis of all function and use and corner case scenarios to ascertain the most optimal power settings when the HIP is functional. Power-related verification attributed at a subsystem level drives power estimation at standalone block level and SoC level for practical product applications. This paper details on the ways to mitigate the costly loss of functional performance and power, and the early development of real use cases, and how the experiment by the power transition test across the multiple blocks was experimented, leading to better performance and power saving. So that the advantage of using a complex power estimation techniques resulted with the most plus minus 0.5% accuracy in power estimation. The fine-tuning techniques deployed based on the new verification approach resulted in a saving up to 30% power consumption on silicon. The fully configured and powered on mobile consumes minus up to 41 milliwatt, 18% less against the planned 50 milliwatt, adding power with the power rate on the consumption 8.44 milliwatt, the 5.86 milliwatt, 30.26%, and the power gated block with minimal functionality to the block was found to consume only 0.58 milliwatt against the planned 0.65 milliwatt, the watt as 11%. Introduction. A systemic approach inculcate the target and efficient and smooth verification flow for the low power simulations for the large SoCs. Power aware verification flow, figure 1. The 1. Analysis of power, voltage, and clock domains. 2. Defining a verification scope. 3. One-time compile and loading the power information of design. And 4. PMI's control and mimic the behavior of the test bench. Power operations, isolations, level shifters and retention, and checkers to reinforce DV. Our SoC consists of 75 power domains, 79 clock domains, and 37 voltage domains, resulting in a mammoth combinations of the power domain switching, which is astronomical to handle and qualify. The hardware description languages do not have the capability to express the power intention of the design, and resulting into the usage of IEEE 1801 standard unified power format at RTL level, followed by a UPF-based synthesis. The power intent of the SoC is defined using UPF 2.0 and the 3.0 and liquefied for standard library cells and hardware makers. The UPF consists of a low power construct like a power domain description, voltage supply port net, and isolation cell logic in retention rules and level shifters and etc. which are used to define the power state of a block. A Liberty file is an ASCII file which provides a standard method for defining library cells that include timing, noise, power, and related input and output characteristics for a design independent of IEEE 1801 file. Simulator can then apply low power semantics to the instances of these cell models at simulation time. The SoC consists of 13 power managers IPs which deployed various low power techniques. Various voltage level for the logic memory's hard micro operating from 0.6 volt to 3.3 volt. So the switcher power supplies power getting using standard library power switches cells, and clock shut off, clock gating when PD power domain is idle. Isolation cells avoid leakage to the nearby PD's power domains. Level shifters sampling signals that cross voltage levels. Retention data saved during power shutoff and restored during power on. And just power off, I think. So this is the figure 1 PA, power verification flow, power oil verification flow. The test bench was developed by compiling the power information for the design by loading the UPF files containing design power information and the Liberty files containing power information for library cells. So the elaboration tool, the requirement, the appropriate IEEE power defined and tool dependent power defined. This discrepancy in the way the tools from the different EDA vendors interpret the IEEE standard result in unexpected issues that consume significant manual effort during the environment bring up. To avoid this feature, our utility to resolve the discrepancy has been developed. The test bench was architectured to mimic the behavior of the PMIC figure 2. The SoC power up and down was achieved by simulating the power boards at the DUT and top using a system verilog model. So the power ports are driven with a combination of dollar supply on or off system tasks and CPU firmware methods which control the power domains of IPL based on the use case of the power manager IP. So the reinforcement through the verification and additional checkers for isolation strategies, level shifter strategies, retention strategies, power switches of the power domains, and the power state table were developed. So this ensures the power intent as desired by the architecture were intact and the UTUT exercised the right power intent. Figure 2 is test bench structure. Section 2 is SoC level power reduction techniques. The active power is directly proportional to the IP activities can be optimized by analyzing the IP activity. The group of such IPs in a design blocks along with the techniques like power scaling, clock gating, and power gating can effectively bring down the active power consumption. Typically, the transition latency increases as the aggressiveness of the power saving techniques increases. The transition latency directly affects the duration required to recover from a power down state. The degree of power saved in a power shutoff is maximum, but it comes at the expense of a higher latency. Based on the requirement for power saving and the IP functional requirement, a three-step approach was implemented to reach the lowest power state. Low power entry. The first step involved getting the IP based on the idle time, which restrict the number of toggles at IP boundary, resulting in a significant reduction in the power consumption. The IPs that are power domain also quiets and perform the low power handshake with the NOC and the power control via Q channel and C channel interface. And a clock shut off. As two-step approach was identified to efficiently gate the clock, the low power entry triggered the clock shut off effects and cutting off the all clocks at the IP boundary. Assertion-based checker was developed to monitor all free running clocks across the SoC based on the clock tree diagram architecture. So the data from the analysis of the checkers resulted in identification more than 100 free running clocks that were brought under the clock shut off logic, resulting in huge power saving. The power gating. The third step in our approach involved the turning of the virtual power rail to power around using the power switch. During the power gating, the signals will be driven to X for simulation purposes, and the outputs are isolated to 0 or 1. The current implementation to reach the lowest power state involves the sequential transition beginning with the entry to low power state and clock shutoff and isolation enable and power shutoff reset assertion. The SoC also supported retention of the memory, few memories and flops through the controllable knobs. And figure 3 is handshake protocol. With increasing complexity, the additional logic and requirement to keep the power consumption low, the need for bifurcating the complete design across multiple controllable power domains becomes imminent. Based on the analysis of the architecture and to support the power requirement of a total of 70 power domains were identified across the 13 blocks of the design figure 4. The complexity of the design and a stringent use case, the scenarios makes the power rail-off and the on-process as critical on power saving technique. Figure 4 is a master and slave configuration to control the different power domain. And the master-slave configuration is handshake are controllable by both handshake hardware and software triggers. To the addition this to the FSM in the design allows controllers to be configured to the different phases of the power domain. Figure 3. The operational stage OPR, clock shutoff CSO, and retention RET. The power shutoff PSO from the different phases, and these phase transition are controllable by software as well. Figure 5. The figure 5 is the power off processes in IP. To achieve the maximum power reduction and enable ease of control, the design was enabled with both hardware and software control mechanism. The hardware control the process is based on an event trigger mechanism. The trigger is generated from a core and security subsystem or registers in always own domain of the targeted subsystem. Based on the event trigger programming, the power down and power up sequence will be initiated. So the two reinforce the verification, the assertions were developed to monitor the change of the intermediate status during the different power stages. So that the hardware control are also supplemented with the software control that take charge of the event and the power transition via APB interface. So the software triggers including register right to the clock controller to gate clock at the boundary of the PLL. The individual power domain control like retention, clock shutoff, and from the power controller, and block logic reset. So the power control in the SoC supports the clock frequency gearing as well, using a programmable AXI interface controlling the clock manager as part of achieving the low power target. So the block level power state transitions are controlled by the hardware trigger, in which a power state is coupled with a combination of low power techniques in different power domains. Figure 6. Figure 6 is the power domain diagram for individual blocks. So the sheer numbers of the instances of the IP, very high complexity, resulting in various challenging tasks for the verification engineers with multiple power domains and rails and controlling a vastly different and independent systems with a myriad of use cases, resulting in using volume tests to be run at SoC level where the simulation times are very high. A few of the most challenging tasks were identified as propagation resulting from incorrect port driver and aligning the power sequence guide with the architecture implementation to get a power consumption to match with respect to the expectation and the requirement. To reinforce the verification and gain confidence, all the tasks developed for the RTS simulation were run with the native low power simulation. This approach opened up a new possibility where the power estimation analysis could be the real use case scenario that will be run on the actual chip. To shift left and mimic the real power gaining scenarios with PG netlist, the retention and isolation strategies were added to the UPF 3.0 that are taken for final synthesis. To avoid S-propagation of isolation cells are used in conjunction with the clamp cells, which can drive the output of the known value. To reinforce the verification assertion, checks were added to the clamping value for the outputs for the retention cells, which are placed in the power domains. The verification is accomplished for the memories flops with the power layoff and power gaining scenarios. To complete the verification, gain battle confidence and code branching expressed to go toggle and FSM and the functional coverage, including low power and SoC level, were taken to the closure within stringed timeline. The region 3, the table 1 SoC level power consumption. The power reduction techniques were experimented in the verification scenarios in combination with the hardware supported method to achieve the power consumption figures as well as per requirement. These initial figures revealed that power consumption was 2.1 times and 3.4 times of the specified values in each of the scenarios. The supports software programming of register for a clock controller, the power controller, and the power pins controller. Based on the analysis of the power pins control and the power consumption from the functional scenarios created, the design architecture was tweaked, resulting in up to 83% power reduction. Table 1. As shown in the above table, the lowest power consuming state reached only when the chip stays idle for a longer duration and the whole chip will take off from standby when the external trigger is received, for example a GPIO trigger. If a block is in idle state, the whole block and power domain will go to the clock gated stage so that the wake up is faster and the functionality is not affected. So based on the idle time duration, the chip goes to multiple intermediate low power stages between IP level clock gating and gearing to the chip level standby. Table 2 is block level power analysis for scenarios. So the block level power reduction techniques, including clock gating (CZ) and clock gear and power gating (PZ). Clock gearing is same CZ, and power gearing and etc. PZ. The block level clock gearing is achieved from the software programming and the register block, which gears the clock control. The different power domains in different blocks are connected to the power rails with the UPF The different power layers and internal power wires are powered on and off by the internal logic, which is controlled by software. The result of trials of various low power states in a block is mentioned in Table 2. The power consumption is further reduced by turning the power rails off from master controller, but makes the whole block functionally off. Another major finding to improve the performance of the power transition is that a software trigger versus hardware triggers transition performance. The analysis showed that the number of the transition required for the hardware trigger transition is only 40 clock cycles, while the requirement for the same transition for the software triggers event in 200 cycles. Since it involves show slow speed at APP clock, the major setback the hardware triggers only approach is the power figures achieved that meet the required value in the particular scenarios. This is the reason to go about the combination of software and hardware approaches to achieve the related power figures. So the chapter 4 is conclusion. So the current verification scope includes features like clock gating and clock gearing and isolation power gating and power rail off and destination test. And the test sequences, the power down and power up is not only controlled by the hardware parameters but also software triggers. From this test result analysis, it was concluded the combination of software and hardware triggers even help achieve the power target with the requirement of performance. In our SSC level standby test and obtained corresponding power estimation report, the master slave power management methodology used in SSC saved the power tremendously for SOC, with one global master power controller and 14 individual blocks with a subsidiary slave controller, helped reduce power consumption during the low power state by the 1/10 of the total power at top. The power transition sequences which were formulated in our low power verification include states in which only one of the blocks is active and others are all in block power down state. The thorough use case testing of the power controller blocks resulted in reducing the SSC power consumptions by a great extent when coupled with the various use cases arising by analyzing the power estimation result from the PTPX. The iterative verification led to a multiple power, low power, multiple low power SSC states with a combination of a shut-off, clock shut-off, and retention and rare supply off. So in the chip standby low power state, block with master power controller is the only one which is active, and the other blocks are all powered down. As the transition to the state has a high latency and multiple intermediate power saver strategies are being formulated involving both the hardware and software control, in which it is expected to provide us the further power saving in the range of 10 to 75% when a functional data path is not required to be run. So this sequence are not being used as is the software teams to develop the final product drivers, and the early silicon power values strongly correlated the power estimation values run on verification scenarios. Okay, yes, thank you. Thank you for your time. See you next time. Sorry. Today I read this paper, a hardware and software integrated power optimization approach with the power aware simulation that SOC. Thank you for your time. See you next time.